Hi everyone. In today's video, we're going to code a recommender system using LightGCN. So let's get started. So LightGCN falls under this category that use graph convolution to create recommender systems. These two methods, GCN and simplifying GCN, use normal graphs to perform update and accumulate for node embeddings. But the recommender systems, they are using special type of graph that's called bipartite graph. This design restriction basically changes everything. So now we will look into how GCN updates node embeddings and how simplifying GCN node update node embeddings. And we will move to recommender systems to see how these two methods are updating node embeddings. So starting with GCN, the update rule in GCN is pretty much straightforward. So we have the normalized adjacency matrix. This is the embeddings at layer K, which is usually the feature matrix, but they are called the input embeddings. And these are the weights at each layer K. So for each layer in GCN, these three matrices got multiplied with each other. And then we apply a nonlinear function like reload. So for all layers, we apply reload. The final layer, we're performing softmax. So for each layer, we do this formula and to get the embeddings for the next layer, and we do it again to get the embeddings for the other layer. But there was another extension for GCN that they saying that the nonlinearity part is not that important. So if they remove the nonlinearity, it will be just a normalized adjacency matrix multiplied by the representations, the embeddings at any given layer and multiplied by the weights. So they change the design to multiply, they flatten it out for the number of layers. They want to do all the layers in a single line of code. So they are flattening out the adjacency matrix and the input representations, which H0, and the weights matrix. Then they are accumulating the adjacency matrix to the power K, and they are using only one matrix for the weights and the input embeddings. So this formula here will give us the embeddings at layer K. You can see how this will change the algorithm and make it faster, because we are not doing the layers one by one. Basically, we are doing all the layers at once. But the most computational part is just multiplying the normalized adjacency matrix. So this is for GCN and simplifying GCN. They are working with normal graphs. You can see that there are no restrictions. Any node can connect to any node, and at the end you get the predictions whether to perform graph classification or node classification. But for the recommender systems, so this is the neurograph collaborative filtering paper. The recommender systems, they are working with this graph, a bipartite graph. Here's the restrictions. It's user item interaction graph. Any user can connect to any item. The connections between users are not allowed, and the connections between items are not allowed. So we have two distinct set of vertices, the user's vertices and the item's vertices. If a user clicked on an item or clicked on a product on Amazon, this would be an interaction. An interaction can be a click, can be a view, can be a scroll. So this is how do we model the recommendation system. And basically this design changed the concept here. So what we are seeing here will be changed because we have two distinct sets of vertices, the user's vertices and the item's vertices. So this is the definition of bipartite graph from a book called Graph Theory, a Problem-Oriented Approach. The definition called the two sets are X and Y, but in this video we will call them the users, U, and items, I. This is a bipartite graph, and this is the adjacency matrix of a bipartite graph. It's a symmetric matrix where users cannot connect to users. Users are only allowed to interact with items. So here you will have all zeros. Once you reach the item column, you will see some interaction with items. And basically this block here is the same as this one, but transposed. So at the top left corner here, it's the interaction between user 1 and item 1. It's the same thing here, the interaction between item 1 and user 1. So it's just like this is the block diagonal. We're just flipping it into the bottom right corner of the adjacency matrix. And one note here is that in the GCN and simplifying GCN and most of GNN papers, including the gravitation, they are using H for embeddings. But in recommender systems, they are using E. When I looked at that at the first, I was confused. I thought E is the edge mix, it's the edge set. It turns out that the recommender system papers are using E for the embeddings, and the GCN and simplifying GCN and even gravitation, they are using H for the embeddings. Just it can be a bit confusing. It's always like that in papers. It is what it is. For the neurograph collaborative filtering, this is the user embedding at layer k plus 1. It's a nonlinear function. Basically, we're multiplying the previous representation, the previous embeddings with the weight matrix. Then we are computing the interaction between users and items using element-wise product. So we are for each user here. So for this user, we will perform element-wise product with this item and element-wise product with this item. Then for these two items, we are multiplying them by another weight matrix here. And the final values will be normalized by the degree of this user and it's the item that interacted with. We will sum all the degrees and we will divide by that to normalize the values. So here's the difference. We have two formulas now. One formula for the user embeddings and another formula for item embeddings. You can see everything is flipped out. First, we will have to multiply the user embedding, then we will have to normalize these values. So now we are calculating the reverse, which is this item that got interacted with by this user and this user. So this is how do we get the embeddings for this item. Now this is for neurograph collaborative filtering, which was an extension of GCN for a recommender system. Now LightGCN, it's basically combines these two. It uses a neurograph collaborative filtering formulas, but it was inspired by simplifying GCN to remove the nonlinearities. So instead of having a sigma here and a W1 here, W1, W2, instead of having the nonlinearity activations and feature transformation, they are just performing weighted sum aggregator to get the user embeddings and the item embeddings. So just summing up, normalizing by the degree of the users and items and getting the new embeddings. And we will get the final embeddings by just multiplying the adjacency matrix for the number of layers. So this is the input, this is the first layer, the second layer, all the way to the kth layer. It's just like simplifying GCN here. So you could see how this will improve the algorithm and how it will speed up the algorithm because we removed all these calculations. So let's take it for a spin and let's move to the code. Before I start with the code, I just want to introduce the dataset, the movies lens 100K dataset. Can find it here on Kaggle. The main item here is data. You have all the 100K interactions. So this is the user ID, the movie ID, the ratings, and the timestamp. Then you have some datasets just for more information. So the genre, info about the users, info about the dataset. So this is the titles, the movie titles, the occupation of the users, and these are the users, just some information about the users. Then we enter the splits. So we have U1 all the way to U5. These are the 5-fold splits to perform 5-fold validation. And we have two splits here. The UA base, which is the training, and UA test for the testing. Another split for the training and for the testing. I used in this notebook, I used this split here. So we will be working on this split. This is the our training data, and this is our test data. I saw other LightGCN implementations. They are just loading the U data and performing just a random split, just having 10% of the U data as a test set and train on the rest. There's nothing wrong with that, but the predefined split by the dataset creators are usually more balanced. So in the UA test, each user has 10 ratings. So this is user 1 and this is user 2. So if we randomly split it, we might end up that some users are not being in the test set. Then we cannot make a recommendation for them. So that's why I use the predefined splits here by the dataset creators, and I did not create a random split. Before I proceed with the code, I just want to mention that I got most of the code by prompting Grok on Twitter, and I used the official implementation of LightGCN and the notes posted by CS224 just to make sure that the code generated is accurate. So this is the official implementation of LightGCN. Here you can see the model. This is the class LightGCN. Moving back to the code, I'm loading the datasets. I'm printing the datasets. This is the main dataset. This is the training dataset with 90,570 interactions, and this is the test set with 9,400 interactions. And these are the movie titles. I'm pretty proud to say that I watched most of these movies on a VHS. So yeah, these are mostly movies from the 90s. At the beginning, we did some mapping because you might see that the users are not starting from 0. They are starting from 1. Also, the movies, they are starting from 1. So we did a mapping from 1 to 943 to 0, 942 for the users, and for the items with the same. And here we map them into train data and test data for user ID and for the movie ID. This is the training data set, and this is the test data set with the new IDs, with the new mapping. Here we're creating a torch tensor for the interactions. It's basically an edge between user ID and movie ID. They should be the same, so 0, 0. This is the train set, 0, 0, 0, 1, 0, 2. Here, 0, 0, 0, 1, 0, 2. Now we're creating the adjacency matrix. So the rows will be the users and the movies plus number of users, because we want to embed the users first, then the movies behind it, then the movies at the end, then the columns, it's the movies plus the number of users and the users. So we want the users, then the movies, and the values will be 1. So this will create as a torch sparse matrix. So these are the indices, which are the rows, columns, and the value will be 1. So this is degrees matrix, which is the sum of the degrees, and this is the normalized values by the inverse square root of the degrees matrix, and this is the normalized adjacency matrix. To visualize the first 10 rows in the adjacency matrix, this is the interaction of user 1, user 0 with the movies. You can see there's no interaction at this block here. This exactly looks like this one here. You would expect a gap before you see the user interacts with items. And this is the user 1 interaction. This is the user 9 interaction. To visualize the heat map or the whole adjacency matrix, this is the heat map, which is, these are the user item interactions, these are the item users interactions, and because we have more items than we have users, you can see that this is not perfectly square because it's longer for the items, but it matches the shape of the adjacency matrix for a bipartite graph. And this is the visualization for the normalized adjacency matrix. You can see some values here. It's very small. So this is the LightGCN class. Here we're defining the number of users, the number of items, the embedding dimension, and the most important parameters are the initialization of the user embeddings and item embeddings using normal initialization. And this is a forward function. We're getting all embeddings by concatenating the user embeddings and item embeddings, and storing that into accumulating tensor. This tensor will accumulate all the values. And for the number of layers, we are multiplying the normalized adjacency matrix with all embeddings. At the end, we're pulling out from final embeddings, we're pulling out the users, we're pulling out the positive items and negative items, and scoring for positive items and negative items, calculating the loss, and then updating again. So this is the flowchart for training a LightGCN. We select the positive items and negative items. Positive items are basically the movies in the training data. And negative items, we're randomly selecting negative items. We're multiplying the normalized adjacency matrix with all embeddings for L layers. Then we're pulling out the embeddings for the users, positive items and negative items, scoring them, computing the loss, then a new iteration. So here is what's going on inside LightGCN class. So we're passing the users of shape 90,000, and the same shape for positive items or for negative items. And we're passing all embeddings, which is the embedding dimension 64 by 2623, which means that there are 943 users and the rest are items, movies. So for the L layers, we're performing matrix multiplication. We're multiplying a normalized adjacency by all embeddings. Then we are accumulating that matrix for each layer. Then we exit the loop and average by the number of layers. Then we're pulling the embeddings from the final embeddings. We're pulling the users and we're pulling the positive items and pulling negative items from movies. We're scoring the positive scores against the users' embeddings, and we're getting the negative scores against user embeddings. These are the scores. So the training objective, we want positive scores to be the higher than negative scores. So to visualize the positive items and negative items, these are the positive items. So this is the training data. This is user 1. He interacted with these movies. And this is user number 18. He interacted with these movies. So these are the training interactions. And these are the negative items. We randomly created those. So if you look at the distribution, this is the true distribution, which are the interactions, the movies in the training data that we selected as positive items and negative items that we just randomly picked. So we are encouraging the algorithm through the loss to maximize the scores for the positive items, which are already in the training data, and minimize the score for the negative items. So here for the hyperparameters, I selected the embedding dimension 64, 3 layers, and this is the learning rate. A number of epochs is 1000, and the lambda for regularization, I selected this value. We need that for the loss. We initialize the model here, and we start a training loop. These are the users. We're pulling them out from the training interactions. These are the positive items. We're pulling them out from the training interactions. And these are the negative items. From number of items, we are randomly selected from those. And we are trying to match the length of the positive items. So once we get that for the model, we're getting the positive scores and negative scores. Then we are computing the BPR loss. So it's our loss is just two parts: the BPR loss and regularization loss. But in the paper, they are using them as one loss. They are calling them all BPR. So the Bayesian personalized ranking, BPR loss, subtracting the negative items from the positive items, you are performing softmax and taking the logarithm for that. And this term here is just the regularization, basically, where lambda controls the L2 regularization strength. So this part here, the subtraction of positive items from negative items, is this part here. And the regularization term is this part here. And we're multiplying the regularization term by the lambda that we already defined in the hyperparameters. So I trained it for 1000 epochs. You could see that we're starting with 0.6 and we're ending up with 0.35. Here is the function for recall at k. Just one note that the movie lens, the split that we are working on, has only 10 items per user in the test set. So the maximum you could go is recall at 10. Even if you go recall at 20, recall at 15, you cannot, it will basically be recall at 10 because each user has only 10 items. For recall at k, we are pulling the user and item embeddings from the model. We are performing matrix multiplication. just to get a giant matrix where each user has a score against each item, and we are ranking these scores and pulling out the top K items. Then for each user, we are pulling out the true items from the test set, and we are mapping the true items with the predicted items for each user, and we're storing that in a data frame. So the total recall is 0.09, which is not that impressive. Actually, it's not that good. So think about it like this. So for each user, for each 10 movies that we recommend to the user, we are not guaranteeing that even one movie is correct. So our recall is less than 0.1. So we cannot get even one movie correct. So I think it has something to do with the hyperparameters, with the split. Maybe the split is challenging. It was selected this way. I don't know, but this is the recall that I'm getting right now, just to see the recall for each user. So for user number 1, we didn't get any of his favorite movies from the test set. For number 2, we didn't get any hit. For number 3, we got 2, and for number 4, we got 2. So this is the recommended compare function. What I'm trying to do here, I'm trying to see each movie, whether it's present in the training dataset for the user, or it's present in the test dataset, whether it was recommended by the algorithm or not. I'm pulling the user and item embeddings. I'm looping over all the items in the test set to get the true test interactions per user. Then I'm pulling the top K items from the predictions. Then I'm looping and filling a data frame with the titles and with the hits, and whether it's present in the test dataset or training dataset. So for user number 3, we said that we got 2 movies correctly recommended for user number 3, title and training and test. For user number 1, we didn't get any recommendation, didn't get any hit from the test set. For user number 2, it was the same thing. For user number 3, we should get 2 movies. This one, Liar Liar, and this one, Conspiracy Theory. And for user number 4, we got 2, Scream and Liar Liar. And for user number 5, we got 1, which is Silence of the Lambs. Yeah, not that good recommendation. If Netflix is doing that to me, I would just unsubscribe right away. There you have it. I recommend a system that cannot get you one movie right. That's it, guys, for today's video. If you find this video helpful, please like and subscribe. By the way, I'll put all the code snippets, all the screenshots in one blog post and share it with you down in the description. Thanks for watching. Bye.